Hola, ¿qué tal a todos de nuevo? Bienvenidos al Seminario de Álgebra, los que están aquí en el salón y en línea también. El día de hoy nos va a hablar Luca Mariot de la Universidad de Twente
Twente.
sobre conexiones entre cuadrados latinos, autómatas celulares y polinomios coprimos. So, thank you very much, Luca, and we're looking forward to your talk. Thank you.
Thank you for this invitation. I'm quite happy to be here with you. And so the idea is that today I'm going to give like an overview of some of the research that I did in my last few years that relate cellular automata, which are like the main computational models that I used in my research so far, and how they are connected to other algebraic structures, in particular Latin squares and coprime polynomials, and also to see what are their applications with cryptography, because also my main research interest is in cryptography. So I also try to use these results, these algebraic results, in order to construct sound cryptographic primitives. So this is to give like a very rough outline of my talk. So we will first start by introducing what are cellular automata and mutually orthogonal Latin squares, and how to use cellular automata for constructing mutually orthogonal Latin squares. And also we will touch upon one of the cryptographic applications that you can obtain with this type of construction, that are secret sharing schemes in particular. And then in the second part, we will move to another object, which are band functions. These are also very important in symmetric cryptography, especially for designing certain stream ciphers and block ciphers components. So we will see how to use a cellular automata to build also band function, leveraging always on the same construction of mutually orthogonal Latin squares that we introduced earlier. And finally, since this construction of band function that we will show in this second part is kind of complicated, because it's you will see it's a little bit of a convoluted root. We will use many different combinatorial and algebraic objects. Then we will also find, or let's say, expose a simplified construction that is based on linear recurring sequences. And finally, we will give some wrap up and some possible, let's say, directions for future research on this topic. So let's start with the first part. So we start, let's say, very broadly by introducing the field of the research field of combinatorial design that started, let's say, already a few centuries ago with research from Euler in particular. But then it became like a full-fledged discipline of mathematics, let's say, mostly in the mid of the 20th century, more or less, because it had like a lot of applications in statistics, specifically for the design of experiments. And in general, combinatorial design theory deal with objects that are called designs. And we define them as, let's say, we have a finite set X, okay? And then we get a collection of subsets of this set here, which we call A. And these subsets are also called blocks. And these blocks need to satisfy certain balancedness constraints. For instance, if we consider the set X of the first 7 natural numbers from 1 to 7, and then we constructed the family of blocks in this way. So we have 1, 2, 3, 1, 4, 5, 1, 6, 7, 2, 4, 6, 2, 5, 7, 3, 4, 7, and 3, 5, 6. Then you can verify that each block in A has, okay, 3 elements. That is kind of straightforward. But moreover, more interestingly, you can see that each pair of distinct elements in X occurs in exactly a single block. And this is also called in the combinatorial design lingo a balanced incomplete block design with parameters 7, 3, 1. And this particular example is also called the Fano plane, because it is connected also with finite projective geometry. And as a matter of fact, you have a nice pictorial representation of this Fano plane that you can see here on the right. So if you put the numbers from 1 to 7 in this particular arrangement, then you can see that each subset of 3 elements from 1 to 7 that we have in our family can be connected by a line, and in this way we are able to construct a plane, so the Fano plane. So this adjacency relation is basically just saying that a number is like connected to another one if they appear in the same block. So like I said, the combinatorial design theory started to be fully developed at the beginning of, or let's say half of the last century. But the first traces of this theory can be dated back to the work by Euler. And as a matter of fact, well, Euler was interested in a lot of different mathematical problems. But one of the problems, one of the riddles in particular that he was interested in was this famous 36 officers problem. And he was asking, okay, assume that we have 36 officers, and each of these officers are drawn from 6 different ranks and 6 different regiments. So is it possible to arrange them for a parade, let's say in the middle of the city, such that they are like on a square 6 by 6, and such that in each row and in each column, there are no repeating ranks nor regiments, okay? This seems a very convoluted or complicated, let's say, problem with no really practical applications. But then actually this is equivalent to asking what we will call mutually or orthogonal Latin squares of order 6. And this has a lot of consequences from the point of view of applications for statistics, for instance, or for coding theory and for cryptography, which is what I'm most interested about. So this is, let's say, mostly a historical note about how this field came to be in mathematics. So now let's start to analyze a little bit more in detail this 36 officers problem. And first we start by defining what is a Latin square. So a Latin square is simply a matrix of size n by n, let's say, such that in each row and in each column of this matrix, we see all numbers from 1 to n exactly once. So each row and each column of this matrix is a permutation of the set square brackets of n, which is like the set of the first n positive integer numbers. So this is an example with order 4. You can see that a Latin square is actually a weaker version of what we are more used to call a Sudoku, because in a Sudoku you have exactly the same properties on the rows and on the columns. Moreover, you also require the same permutation property on the subsquares. So in this particular example here, you can see that this is also Sudoku because here we have 1, 3, 4, 2 in this subsquare. And also here in this subsquare, we have all 4 numbers, and also in this subsquare, and also in this subsquare. But actually, in our case, we are just interested in the Latin square property, which is stating that this permutation constraint holds only on the rows and on the columns of the square. So quite simple up to now. Now we complicate a little bit more the things because we introduce orthogonal Latin squares. So we consider 2 Latin squares of the same size, of the same order. And then we say that they are orthogonal if by superposing them, so we put one on top of the other, and then we will get pairs of numbers in each cell. And then we are going to see all pairs of the Cartesian product, so n by n. So in this case, all pairs, including the numbers from 1 to 4, which are 16 in total, because we have 4 by 4 possible combination. And we see each of these pairs exactly once. So it means that the superposition of these 2 Latin squares is again a bijection or a permutation, but this time over the Cartesian product of the first n positive integer numbers. So this is the notion of orthogonality of 2 Latin squares. And then if we have a set or a family of n Latin squares which are pairwise orthogonal, so if we take any pair, they satisfy the orthogonality relation, then we call this set, we denote this set as an n-moles, where moles is an acronym for mutually orthogonal Latin squares. So what Euler was interested in with the problem of the 36 officers was basically to find a pair of orthogonal Latin squares of order 6. So this is, let's say, what I was mentioning in the beginning, that we would touch upon a cryptographic application. So why are we interested in mutually orthogonal Latin squares for cryptography? So there exists this type of cryptographic primitives called a KN threshold secret sharing scheme, where you can imagine the following situation. So you have a dealer, and this dealer wants to share, let's say, a secret information, for instance, a cryptographic key, with a certain set of participants. So in this case, we have three possible participants, P1, P2, and P3. And in order to do this, he applies the dealer this protocol, this secret sharing scheme protocol, and he computes some shares of the secret information S, and we call them B1, B2, and B3, and he distributes them to the participants P1, P2, and P3. And then the scheme is such that any possible combination, for instance, of two participants in this case, if we put a threshold k equal to 2, is able to reconstruct the secret by combining together the shares obtained from the dealer. So B1 and B2 can reconstruct the secret, B2 and B3 can reconstruct the secret, and B1 and B3 can also reconstruct the secret. So any combination of at least two participants out of three can reconstruct uniquely the secret. On the other hand, if you take less than two shares, then the corresponding set of participants is not authorized to compute the secret. And in particular, they cannot gain any information on its value. So this is why it's a secure scheme. So it is actually called perfect because the participants, if they don't reach the specific threshold k, then they cannot really gain any information. So any possible value of the secret is equally likely. And as a matter of fact, you can show, but we are not going to see this into details, that a secret sharing scheme where the number of required participants in order to reconstruct the secret is 2, so a 2n secret sharing scheme, is equivalent to a family of n moles, so to a family of n mutually orthogonal Latin squares. So this is, let's say, some cryptographic motivation of why we want to construct mutually orthogonal Latin squares. There are several ways to do that. What I focused, let's say, in the previous years to as a means to construct mutually orthogonal Latin squares are cellular automata. So cellular automata are, let's say, a parallel computational model. And usually you see them in the literature described as a type of discrete dynamical system. Actually, here we are not interested in dynamical questions, let's say in questions about the dynamics or the long-term dynamics of a system composed by cellular automata. We are just interested in studying cellular automata as a particular type of algebraic mapping. So for the sake of our presentation, we can consider them as vectorial functions. So let's say that they are vectorial functions over a finite field of order Q, so FQ. And we have, in particular, the input space of our cellular automaton, which is a vector space over this finite field FQ of dimension n. So it means that the input of our cellular automaton will be a vector of n components, where each component is an element of the finite field FQ. And then this mapping here, so it is mapping over another vector space of m coordinates, in this case, also of dimension m in this case. But the thing with cellular automata is that the mapping can be described by a single coordinate function, and then we apply it in a shift invariant coordinates. What does it mean? Well, it means that if we take, let's say for the sake of example, we have q equal to 2, so we will have the finite field f2, which is the binary field with 0 and 1 as element. Then we take as an input space size 6 cells, and we take also what is called the diameter as a parameter, so d equal to 3. And then we define the so-called local function of our cellular automaton. So this local function is defined as a function of d variables, so 3 variables in this case. So we will have a function of 3 variables or 3 cells, which in this specific example is simply the XOR, so the sum modulo 2 of the 3 variables in the argument of our function. So Si XOR Si plus 1 XOR Si plus 2. So XOR or sum modulo 2 is the same because we are working on the field F2. And the idea is that if we start, we can have 2 different situations with cellular automata. So the first one is when we consider a no-boundary cellular automaton. And in the no-boundary case, we start with our input space of 6 cells, and then we start by applying the local rule f to the first set of 3 cells. We compute it, so it will be the XOR of the first 3 cells, so 1, 0, and 0. The result is 1, so we put a 1 in the output. Then we shift this one place to the right, this window of diameter 3, And then we compute again the local function over this neighborhood that is composed of 0, 0, 0 in this case. So the result will be 0. And then we continue again by shifting one place to the right. So again, f of 0, 0, 0, which is 0. And finally, f of 0, 0, 1, which is 1. So the idea why it is called a no-boundary cellular automaton is because basically we are applying the local function only up until we have enough right neighboring cells on the right. So here we can just apply it up until we arrive at the fourth cell. So this is the no boundary CA case. In the periodic case, instead, we are considering the input space as a ring in a certain sense, so with circular or periodic boundary conditions, which means that the first cell is following the last one, and likewise, the last cell is preceding the first one. So we can compute, in this case, the local function of each possible cells in the input, which means in particular that when we arrive here, for instance, at the last cell, we will apply the local function over 1 plus the first 2. So we are going back in a wraparound fashion, which means basically that the output space of the cellular automaton is not shrinking. And anyway, for most of our presentation, we will be interested actually in the no boundary cases. So in this case, we will apply the local rule, and then we will have an output space that is smaller than the input space. But this is not a problem because we don't want to iterate this cellular automaton as a dynamical system. So it means that we can we are just interested in particular in applying the local rule just in one time step. Okay, now, in order to get, let's say, this is just a recall of what is the definition of two orthogonal Latin squares, but we already introduced that earlier. So how do we construct Latin squares or orthogonal Latin squares using these no boundary cellular automata that we introduced earlier? So we focus on a particular case, which is when the local rule is defined as a bipermutive rule. What does it mean? It means that the function f, computed over neighborhood of diameter d, it has the following form. So it will be the first variable x1 summed with a function of the central d minus 2 cells, so from x2 up to d minus x d minus 1, plus the value of the last cell on the rightmost cell in our neighborhood. So here the plus sign is to be meant over the finite field fq over which the cellular automaton is defined. So this is the, let's say, form of a bipermutive rule. So it means that it is quasi-linear. It is also called because it is linear in this variable here and in this variable here. And then this function can be anything, so also a nonlinear function. So in particular, we call this, just for the terminology, this phi, this central function here, we call it a generating function of f, because from it, you can also recover what is the original bipermutive function by just adding the leftmost and the rightmost cells. And then the first result is that we can construct a Latin square. So we want to get orthogonal Latin squares with cellular automata, but first we need to see how to construct Latin squares. So we use a no boundary cellular automaton over the field fq with an input space that has size twice d minus 1, so where d is the diameter of our cellular automaton. So it means that if we apply, as we defined our cellular automaton earlier with that local rule, starting from something that has length 2 times d minus 1, we will get an output block of length d minus 1 in the no boundary case. And now, if we have the constraint or the property that the underlying local rule is bipermutive, so as we defined it above here, then we can construct a Latin square in the following way. So we will have a Latin square of size q to the power of d minus 1, so where q is the order of our finite field. And then we use the input space to index the row and the column of this square. In particular, we use the left half of the of the input space, so the first d minus 1 cells, to index the row. So for example, if we have like q equals to 2, so we have a binary representation, it means that this first block of d minus 1 cell will be the binary encoding of a natural number, of course, and then we use this natural number as the coordinate of the row. And then we do the same also for the second part, so the second half of our input space, but this will be used to index instead the column of our square. And finally, the result of the cellular automaton obtained by computing the local rule over this input space here, input vector here. So this output here will be the entry that we are going to put at this coordinate x and y. Okay. So if this is the case that the underlying local rule is bipermutive, then this square here is indeed a Latin square. As an example, we can consider a very small cellular automaton. So we have a cellular automaton of size 4, so 4 cells over the finite field F2, so the binary case again. So we are getting 2 cells in output, in particular if we consider a diameter equal to 3, as in the first example. And as a matter of fact, we are also considering the same rule, the same local rule for our cellular automaton, so the XOR of all 3 cells in the neighborhood. This is also called rule 150. It's not important. It's just a way of encoding the rules of cellular automata using their truth table. So you encode the truth table of a cellular automaton in decimal. And in this case, if you have XOR X1, XOR X2, XOR X3, and you take the truth table, the decimal encoding of this truth table will be the number 150. Anyway, if we consider the encoding for pairs of bits, in this case, this one, in particular, 0, 0 is mapped to 1, 1, 0 is mapped to 2, 0, 1 is mapped to 3, and 1, 1 is mapped to 4. Then by computing all possible 16 combinations of input vectors, then we can fill a square 4 by 4. And since this rule here is in particular bipermutive because we are summing the leftmost and the rightmost variable modulo 2, so it is satisfying the definition of a bipermutive rule, then we will get this specific Latin square. So this is the way how, with any bipermutive rule, you can construct Latin squares using cellular automata. So this is the first step. What about the second step? So how cellular automata are used to construct orthogonal Latin squares? So here we need to go a little bit more into specifics. So we need to consider cellular automata that are not only bipermutive in their local rule, but they are also linear, which means that we have like the local function that is defined as a linear combination of the cells in the neighborhood. So for instance, rule 150 that we saw before is just a sum modulo 2 of all cells in the neighborhood. So it is a linear rule. And then when you consider these linear combinations in a linear rule, then you can also associate a polynomial in a quite natural way to this rule by just using the same coefficients in the linear combination as the coefficient of this polynomial for increasing powers of the unknown x, or let's say capital X in particular, to differentiate it with the variable used in the local rule. So we can associate a polynomial of degree d minus 1, in particular, where d is the diameter of the local rule. And also we can associate a transition matrix of this cellular automaton. This will have size n minus d plus 1 rows and n columns. And it has this specific form here. So we start with the coefficients of our, let's say, of our local rule, of our linear local rule. And we put them here on the top left. Then we fill the rest of the row with zeros. Then we put a 0, so we shift one place to the right, and then we put again all the coefficients from A1 up to AD. And then we fill the rest with zeros. Then we shift by 2 places with zeros, and then we put again our linear coefficients, and then we continue like this until we are right here at the end. And then one can show that the computation of a cellular automaton rule, when the local rule is linear, basically amounts to the multiplication of the transition matrix MF by the transpose of the input vector of the cellular automaton. And as a matter of fact, you can show, it's quite easy to show that a linear rule is also bipermutive if and only if the leftmost and the rightmost coefficients here in the linear combination are not null, because this is the only way in which you can take like a bipermutive rule to satisfy the definition of a bipermutive rule. Now that we have also this under our belt, we can see how we can construct mutually orthogonal Latin squares with linear bipermutive cellular automata. So cellular automata whose rules are both linear and bipermutive. So we call this LBCA for short. And the neat result that we obtain in this case is that if you have a set of linear bipermutive cellular automata, so they are always of size 2 times d minus 1, and then they will give us an output of size d minus 1, so as we saw in the construction of a Latin square. And then this family of linear cellular automata will generate a family of t mutually orthogonal Latin squares, if and only if their associated polynomials are relatively prime. So what does it mean? It means that the greatest common divisor between the polynomials associated to each of these cellular automata is always 1. So it means that they are coprime. This is an example that you can see here by using, again, the Latin square that we used in the previous example with rule 150. And then the Latin square that you obtain with rule 90, where instead you just XOR the leftmost and the rightmost cells in the neighborhood. So x1 XOR x3. So you get this particular Latin square. If you do the superposition, then you will see that actually these two Latin squares are orthogonal. And the reason is precisely because the two associated polynomials in this case would be 1 plus x to the power of 2 for rule 150, and 1 plus x to the power of 2 for rule 90. And indeed, if you are going to compute the greatest common divisor of these two polynomials, this will be 1, so they don't have any factors in common. And this means that you get like two coprime polynomials, so the condition of this theorem is satisfied. So the bottom line is that with this construction, you can just say, okay, if I want to construct a set of mutually orthogonal Latin square, of t mutually orthogonal Latin square, then what I need is just a set of t coprime polynomials that are pairwise coprime in particular. If they are pairwise coprime, then it means that they will give rise to a set of mutually orthogonal Latin squares because of the theorem so earlier. Now, there are a few questions that are, let's say, kind of natural to ask ourselves. First of all, if we set, let's say, the size of our Latin squares, so in particular the diameter of the cellular automaton, or equivalently the degree of the associated polynomials, then what is the maximum number of coprime polynomials over the finite field FQ? So how many orthogonal Latin square pairs we can construct with linear cellular automata? And this is actually an interesting, let's say, problem. If you consider it in the case of Q equal to 2, so finite fields of order 2, or we are in the binary case as usual, then you can notice that the number of orthogonal Latin squares can be described by this recurrence equation, and which give you like this specific integer sequence. So 0, oops, sorry, I went a little bit further, yes. So you start from degree 1, then you will get 0 Latin squares orthogonal with cellular automata, and then if you get like d equal to 2, then you will get 1 pair, etc., etc. So you have 0, 1, 5, 21, 85, etc. This is all described by this recurrence equation. And the nice thing is that when we prove this theorem here, so this recurrence equation, we didn't know about this specific recurrence, but actually it is already known in this online encyclopedia of integer sequences. It has this specific code here, and it is indexed there because it is connected with a lot of other number theoretic and graph theoretic problems that have nothing to do with Latin squares and cellular automata, to be sure. But actually, yeah, it's interesting to see how the same recurrence equation is describing very different facts in number theory or graph theory. Specifically, like it is also related to the so-called Collatz conjecture, because you can prove that if you start like from any number in this sequence, then the Collatz conjecture will actually, let's say, converge to the periodic solution 1, 4, 3, etc. This is actually instead a conjecture, so an open problem if you start from any other number. Okay, so let's move to the second part of the talk. So now we know how to construct mutually orthogonal Latin squares with cellular automata, and so by consequence, in turn, we can also construct threshold secret sharing schemes where we have two participants at least required in order to reconstruct the secret. Now we focus instead on another object using cryptography, which are band functions. So band functions are a particular type of Boolean function. Boolean functions are simply mapping of the type, okay, we have a set, or let's say a vector of n bit, so n either zeros or one, and then we are giving in output a single bit, so just either 0 or 1. And they're used a lot in the design of stream ciphers. For instance, when you want to construct a pseudo-random generator that is stretching, let's say, an initial short secret key into a long pseudo-random stream is called, that is then XORed bit by bit with your plaintext, and then you get the corresponding ciphertext as an encryption. Or they are also used in block ciphers where instead you're not encrypting one bit at a time, but let's say several bits that are bundled in blocks of a specific length. So the idea is that here these constructions of stream ciphers and block ciphers relies on the properties of the Boolean functions that are involved in the pseudo-random generator, for instance, or in the S boxes that you see here that are vectorial Boolean functions. So a Boolean function can be represented like quite easily using the truth table. So we just specify what is the vector that is, let's say, defining the output of each possible input vector. So if we have 3 input variables from 0, 0, 0 up to 1, 1, 1 as possible values, then for each of these 2 to the power of 3, in this case, values, we are going to explicitly state what is the corresponding value, either 0 or 1. So this is the basic representation of Boolean functions. On the other hand, in cryptography, you're also interested in studying what is called the Walsh transform of these Boolean functions, which is a kind of a discrete Fourier transform. And it is particularly useful because you are expressing the truth table of F in terms of correlations with linear functions. So the functions that are just an XOR of a subset of the input variables, let's say. So this is the specific formula for the Walsh transform, but we won't need it. So this is the same Walsh spectrum that you would get if you apply the Walsh transform to this specific truth table in this example here. Now, band functions, they are defined, they are specific kind of Boolean functions, and they are defined as those functions where each Walsh coefficient is equal to either 2 to the power of n divided by 2 or minus 2 to the power of n divided by 2. So this is important because basically you can show that these band functions are the farthest as possible from linear functions. So they have the maximum possible nonlinearity. And nonlinearity is an important property in the design of stream ciphers and block ciphers, because you don't want your Boolean functions in a stream cipher or a block cipher to be easily approximated by linear functions, so to be highly correlated to linear functions. So band functions are actually interesting in crypto because of this fact that they reach the highest possible nonlinearity. Here you have an example with 4 variables, because actually band functions, you can show that they exist only if the number of variables is even. Because of course, in the Walsh transform, as it is defined, we can only get integer numbers as coefficients. So this particular coefficient here will be an integer number only if n is an even number. And moreover, besides being highly nonlinear, they are also unfortunately unbalanced. So they don't have in their truth table the same number of zeros and ones. This is also an important cryptographic property. It is not satisfied by band function, but still you can use band functions to, let's say, construct, let's say, balanced functions that are also highly nonlinear. So this is the reason why we are still interested as a theoretical object to construct in band functions. So yeah, this is, let's say, a small intuition of why they are called band. And the fact is that, yeah, they are band because they are not straight. So we consider functions that are linear to be straight. And then those that are, let's say, the farthest possible from being linear, we call them band. And this has some relationship also to some coding theoretic questions, in particular to the covering radius of Reed-Muller codes. But okay, we are just mentioning it and not delving into the details because of the sake of time. So there are several constructions of band functions around in the literature. So the first, let's say, and most known one is the so-called Majorana-McFarland functions, or class of functions, where you define a function f in this way. So you will have two arguments, so x and y, and you combine x and y in the following way. So you compute first the scalar product between x and a permutation of y, so any bijective function over the vector y. And then you XOR this with any other function g computed only on the second argument y. You can show that in this way you can always get a band function. And this is, let's say, a very large, it gives you like a very large class of functions, because you can just enumerate them by enumerating all possible permutation over this vector y. Another class, which is, let's say, more interesting for us, is the, let's say, the class of partial spreads. And in partial spreads, we have a family of spaces, of n-dimensional subspaces. So let's say that n is the number of variables of our Boolean function is defined at twice m. So it is an even number, because otherwise we can't get band functions. Then if we have a family of m-dimensional subspaces, and these subspaces are such that their intersection, their pairwise intersection, is trivial. So it means that if you take any two m-dimensional subspaces and you compute the intersection, you will get only the null vector, because of how it is defined, a trivial intersection in linear algebra. Then you can use this family, which is also called a partial spread, to construct a band function in the following way. So you construct the support of the function, which is just the set of input vectors which map to 1 under the function f. And then you compute the union of all these families, let's say, stripped of the null vector. Okay, so you just don't consider the null vector inside the support of this function. In this way, you can get another type of band function, which are called partial spread band functions. So in particular, in order to show now how we can get band functions from cellular automata, we need to pass through another combinatorial object, which are Hadamard matrices. A Hadamard matrix, a matrix is simply a matrix of size n by n, where the entries are either plus or minus 1, so you can just denote them as either plus or minus, as in this figure. And this square matrix is such that it is orthogonal in the linear algebraic sense. So if you multiply H by its transpose, HT, then you will get the identity. Then you have a necessary condition on the existence of Hadamard matrices, that is that the size of the matrix must be either 1, 2, or a multiple of 4. But actually, this is a necessary condition, but it is not known whether an Hadamard matrix exists for every possible multiple of 4. So this is still an open question in the theory of Hadamard matrices, and one of the most famous conjectures in discrete mathematics, I would say. So yeah, the fact is that Hadamard matrices are connected to band functions, but we are not going to delve into the details of how of why this is the case. The idea is that simply you can define a Hadamard matrix. If it is a Hadamard matrix of size 2 to the power of n times 2 to the power of n, then you can compute, let's say, a function f in this way, and then you can show that this is indeed a band function. So here you have an example with the simplest possible band function of two variables, which is just the multiplication of x1 and x2 modulo 2. And then you obtain the following Hadamard matrix, or vice versa. You can start from this Hadamard matrix and obtain the band function x1 times x2. So in particular, Hadamard matrices are also related to mutually orthogonal Latin squares, because you can show that if you have a set of T mutually orthogonal Latin squares, then you can construct what is called an orthogonal array. And an orthogonal array is simply, let's say, starting, for instance, from these two Latin squares that are orthogonal. We saw them earlier, so they are done with the Cellular Automata 150 and 90. Then you start by making this rectangular matrix of size 16 rows and 4 columns, where in the first columns, so the first two, you just put all pairs in lexicographic orders. And then in the third column, you will linearize, let's say, the first Latin square, so L90. So you read them like 1, 2, 3, 4, and then you fill the first rows here, 1, 2, 3, 4. Then you take the second row, 2, 1, 4, 3, and then you fill this with 2, 1, 4, 3. And then you continue like this until you arrive at the bottom. And then you do the same also for the fourth column. So this is called an orthogonal array, because if you take any subset of 2 columns, then you will see each pair of numbers, so each ordered pairs of the Cartesian product exactly once. And there is this theorem by Bush in 1973 that is saying that if you have like a set of T mutually orthogonal Latin squares, then using this orthogonal array characterization, you can construct a Hadamard matrix of size 4T square. Okay, this actually I will skip because it's not really important for the sake of our discussion. The idea is that now, in order to go towards conclusion, and probably I will just skip the last part because, okay, we are already a little bit, not over time, but we are going let's say, to elapse our hour. So we are going to show just how to use linear cellular automata to construct band function through Hadamard matrices. So the question is, if we get linear cellular automata, we can get mutually orthogonal Latin squares, but then these mutually orthogonal Latin squares can be used to construct band functions. So we know for sure that we can construct at least Hadamard matrices, because we saw earlier in the slide that there is like that theorem saying, okay, if you have T mutually orthogonal Latin squares, then you can construct a Hadamard matrix of size 4T square. The problem is that not all Hadamard matrices correspond to band functions. So in particular, if you set now the size of the Hadamard matrix 4T square equal to the size of the truth table of a Boolean function, so 2 to the power of n, then we can define a set of mutually orthogonal Latin squares by using T coprime polynomials with cellular automata, as we did in the first part of the talk. And the degree needs to be d minus 1, which we denote by b. So in the end, in order to have all the equations or relations satisfied, we need to have, let's say, these relations satisfied. So 2 to the power of LB, where L is the extension of the finite field, if we get a finite field of characteristic 2. And in this case, we will get, if we go through logarithms, that LB is equal to 1 plus the logarithm in base 2 of t. So since both L and B, which are denoting respectively the size of the extension of the finite field and the degree of our polynomials, they need to be integers. So it means that our number of coprime polynomials will be 2 to the power of a number, so W in this case, where W is any natural number. So now the final theorem is that we can construct indeed a Hadamard matrix starting from a set of linear bipermutive cellular automata. And we define, let's say, a Hadamard matrix using Bush theorem, so that is already granted by that result. But actually, if we define the support of a new function f in this way, so we say that f of x will be 0 if the argument is 0, so that is easy. Then we say 1 if x is not equal to 0, and moreover, we are able to find a cellular automaton in our family, so let's say fk, such that fk computed over x is equal to 0. So it is like in the null space of our linear cellular automaton, and 0 otherwise. Then in this case, it's you can show that the resulting Hadamard matrix is indeed a band function. And this is an example, let's say, to wrap everything up. If we still stick to the same 2 rules that we introduced in our examples of cellular automata, so rule 90 and rule 150, so there are associated polynomials where 1 plus x to the square and 1 plus x to the square. And these are the corresponding Latin squares. If we linearize them and we take the orthogonal array, then by discarding, let's say, the first 2 columns where we had all pairs computed with in lexicographic order, we will get this particular orthogonal array. And this particular orthogonal array we use to construct a Hadamard matrix, which has the following form here. Then, if you take either the first row or the first column of this matrix, and then you transform it from the -1 or +1 entries to 0 or 1 in order to have a Boolean function, then this truth table will be indeed a band function that has this particular algebraic form. So again, to wrap it up in a whole package, we start from coprime polynomials, such as, for instance, the polynomials that we saw in the example here. Then from here, we use the construction with cellular automata to get 2 Latin squares in this case, or t Latin squares in the case we are having more coprime polynomials. And then we do that since they are pairwise coprime, then they will give us orthogonal Latin squares. And then from there, we will get a Hadamard matrix that is related to a band function. And then again, you have existence questions and counting questions. So actually, you can show that for any possible n, it is possible to construct these band functions only if the degrees of the polynomials are either 1 or 2. So for more than 2, you're not able to construct these functions. And also for counting results, then after you say, okay, I constrain my degrees of the polynomials to be either 1 or 2, then what is the number of CA-based band functions? So band functions constructed with cellular automata. And okay, so as I said, this part here is just a simplified construction, so we won't go into the details because it's still retelling the same result, but in a less complicated way than here. So here we use like a lot of objects like coprime polynomials, orthogonal Latin squares, orthogonal arrays, Hadamard matrices, and in the end we get band functions. Here instead, the gist is that you can just use or define cellular automata as a specific kind of linear recurring sequence. So a recurrence equation that is also linear, and this can be computed quite efficiently using the so-called linear feedback shift register. And then again, the same result hold. So you are still able to get a band function, which moreover you can prove to be in the partial spread class that we introduced earlier. So to conclude, basically let's say, most important findings of this research thread is that you're able to construct, okay, mutually orthogonal Latin squares using coprime polynomials through linear cellular automata. And this is interesting already for crypto because you can do like secret sharing schemes with that, for instance. And then we came up with a complicated construction that can be simplified. We didn't go into the details, but again, it can be simplified. Indeed, it can be simplified. And this construction is a construction of band function that leverages the construction of cellular automata with Latin squares, passing through Hadamard matrices and orthogonal arrays. And finally, these band functions are interesting, let's say, from a theoretical point of view, because they coincide, if you consider like the case of degree 1, with a very well-known partial spread class that is called PSAP, where AP stands for affine plane because it has some relation with finite geometry again. And instead, for degree 2, possibly many of these functions that we found are not in the class PSAP, so they might be also more interesting from a theoretical point of view because maybe they are, let's say, they are unknown functions that have not been discovered before by mathematicians. So these are indeed like the open problems. So to check whether the functions that are obtained with degree 2 are really new, and also from a more computer science point of view to implement these band functions using the parallelism of cellular automata, in particular with their characterization of linear feedback shift registers when they are linear. And yes, this concludes my talk. So thank you for listening. And if you have any questions, I will be happy to answer them. Thanks.
Thank you very much, Luca.
Thank you.
¿Alguna pregunta? ¿Comentario? ¿Alguna pregunta en línea también? Okay, so I wanted to ask you a couple of things.
Yes.
So first, I saw that you mentioned before in the result of that you get from 2 linear CA that you get a band function. You had a
Yes.
remark there that you didn't comment, saying that it was essential to be linear, and that it was the first. It caused you the first
Oh
rejection.
yes,
So
indeed.
that
This is a leftover from a previous slide in another presentation where I was also telling like the story of how it went with the publication process of these results. Uh,
right.
for the part of mutually orthogonal Latin squares with cellular automaton was kind of easy, so we published it on design codes and cryptography. The part
Uh-huh.
on bent functions instead was kind of a bumpy ride because in the beginning they were saying, okay, we had the complicated construction, and then they were saying, no, actually you made an error in the first, like when we were, let's say, proving this theorem.
Uh-huh.
And
Uh-huh.
you were saying that it could hold also not only for linear cellular automata. Actually, you really need the fact that the cellular automaton are not just bipermutive giving orthogonal Latin squares, but they really need to be linear. Otherwise, this result does not hold. You can find a counterexample indeed. And then from there, yeah, okay, this was the first reject, and then we had many other not rejects, but a lot of revisions with design codes and cryptography, where we got into like let's say a discussion with one of the reviewers that was, let's say, the most enthusiastic about this work. But then he was also saying, okay, but you need to rewrite it from scratch because indeed, like, so it's very nice because probably you found like a new class of band functions, but then you're like enshrouding, so hiding all these results with all this stuff on cellular automata, Latin squares, and Hadamard matrices that, in retrospect, in hindsight, they are not really useful. So if you want to focus on band functions. And so we started with a lot of minor revisions in order to, let's say, satisfy this reviewer and finally have the publication on design codes and cryptography. And now, indeed, the paper looks much more, let's say, simple to read.
So finally, that result appeared in the. It's already published. That one.
Yes. So
Okay.
this one is published and it's referenced here. So you can see this paper here in particular.
Okay. Okay.
Here you have the DOI, but it has already been assigned also to an issue of design photography. So it's been published not only online, but also on paper, let's say in print.
Okay, great, thank you. And you, well, just another comment that I tell you is it's interesting all this process because okay, you start with two linear cellular automata and then you get a bank function that
Yeah.
can be seen again as a cellular automata, right? Just the local rule is just a bank function, like you can call
Oh
it a,
yeah, sure. You can
a band.
also consider it as a bent function in a cellular automaton construction that you could use, for instance, in uh, where was this here, like in a block cipher when you're interested in constructing S boxes, so vectorial Boolean functions. One approach is to use cellular automata, and then you want to that the local rule of the cellular automaton satisfies good cryptographic properties such as high nonlinearity given by band functions. Then again, you can't use them directly because band functions are not balanced, and this is also important. But still, you can turn a band function into a balanced one that is also highly nonlinear.
Ah, right. Okay. Okay, great. Thank. Yeah, I thought that was interesting because I was wondering if there are any properties that, for example, this property of that the local rule is a bank function, if it has reflects in another properties of the cellular automata in general. But
Yeah.
well, I don't know. I suppose maybe you know anything
Uh,
about that.
Actually, no. I mean, I had several ideas in mind in the beginning because when I was trying to single out this result, I thought that there were like a lot of other properties that maybe could apply or characterize this bendness. And actually, indeed, after going through the simplification with linear recurring sequences, then you really see that it's very constrained as a construction. So you really need linear bipermutive cellular automata whose polynomials are coprime, because this is related to the fact that, let me see, it was here, that when you consider like the subspace generated by these polynomials as linear recurring sequences, then they form a partial spread. So they have like a family, the corresponding family of subspace of these linear recurring sequences have pairwise trivial intersection, and so you can construct a partial spread function. So it's highly specific as far as I saw until now.
Great. Okay, well, thank you very much again, Luca.
Thank you. Thank you a lot. Thanks for your attention. It's been a pleasure.
Thank you. Thank you very much. See you. Keep in touch. See you soon.
Yeah, keep in touch and see you soon. Bye.
Bye. Bye.